Welcome to theme 3.3, where we are going to discuss the fundamental theorem for line integrals and how it implicates things for our vector field line integrals. So the theorem basically states that if we take the line integral of a gradient vector field of a function, then it will be equal to the function at b minus the function at a. Let's say your function is a function of x and y, then if your line integral for your gradient vector field is done between a and b, then the integral will be equal to the function of your gradient vector field minus at b minus the function at a. So that's just basically also equal to this. So usually we would have that our gradient vector field dot producted with our r prime t function. So this would also be then equal to this, according to the theorem. If we have a conservative vector field f, we know that it has some gradient, it's equal to some gradient vector field, and that gradient vector field has a function f. So it would be like this. So the line integral of f would be equal to the line integral of the gradient vector field, which if f is conservative, and then that integral of the gradient vector field would then be equal to the function of the gradient vector field at b minus the function at a. So that's just how it ties together. But how do we know that f is conservative? Just keep that thought for a while. So what we need is the potential function, which is f, and we need we need parameterization of the curve and all the coordinates for x and y. So let's say we had a curve like this. When we work between a and b, it doesn't matter what curve it follows, but if your f is conservative, then that line integral will be equal to f at b minus f at a. It doesn't matter what curve you follow. So a conservative vector field is independent of path. So let's get some definitions of different types of curves. Let's start with a simple curve. So a simple curve basically just means that it doesn't cross itself. So that would be like this curve and that curve. But these two curves cross themselves. A simply connected region. So for a simply connected region, that just means that all points enclosed in a simple curve within D should only be from D. So there shouldn't be a hole, like if this line goes through D, that some of the points are from this region. So all the points on a line going through D should be connected. So no holes at all. That would mean that it's a simply connected region. A connected region means any 2 points in the region can be connected by a path that is within the region. So that just means that any point can be connected to another point in the region. So another theorem states that if f, which is a function, is continuous on an open connected region, and C is a piecewise smooth curve in D, which is the open connected region, then the following statements are equivalent. We then say that f is conservative because f is then equal to a gradient vector field, and we know that the line integral is independent of path. So it doesn't matter which path it follows, as long as it goes from A to B, it doesn't matter. And then that the line integral of f is 0 for every closed curve. So this all just means that if you have a function that is continuous in a certain open connected region, and C is a curve within this region, then if you want to have a vector field in that curve, it would be conservative if it is obviously the gradient equal to the gradient vector field of that function. So now we go back to that question I asked you. Well, how do we know if the vector field is conservative or not? So if f is equal to pq on an open, simply connected region, then f is conservative when the following is true. So if you take the partial derivative of p towards y and the partial derivative of q towards x, if those two partial derivatives are equal, then we say f is conservative. So that's just a test that you can run to see if f is conservative. Let's have an example of how this exactly works. Let's say f is equal to 2xy and 2xy. So then the partial derivative of p towards y is 2x, and the partial derivative of q towards x is 2y. So we know that the vector field is not conservative because the partial derivatives are not equal to each other. Let's take another example where f is equal to x squared plus x and y. So if we take the partial derivatives of p and q towards y and x respectively, we'll get that both of them are 0. Therefore, this is a conservative function. Now, if it's conservative and we want to use this fundamental theorem of line integrals, how do we find a potential function for f? Now, let's say f is this conservative vector field, which is x squared plus x and y. So this would mean that this is the partial derivative of f towards x, and this is the partial derivative of f towards y, right? So let's say we integrate this partial derivative towards x. That should, with regards to x, that should give us our f of xy function. And then if we derive f of xy towards y, it should give us our partial derivative towards y, which is then g prime y. So then we know that g prime y is equal to y, because f of y is equal to y and g prime y. So this is how we get to this equation. And then if we integrate this part to get g of y, because that's what we're looking for in this f of xy equation, then we get it as half y squared plus a constant. Remember this constant because it is important for the answer to be right. And then if we plug in this g of y function back into our f of xy function, we get the full and complete function of f. So that is how you get a potential function for f if you have two variables. Now let's say that your vector field is line integral is for a curve from 6,2 to 8,3. Note that it doesn't matter what type of curve you're using. It matters whether it is independent of path or not. So we've already calculated previously that what our f function is. So now we can use the fundamental theorem of line integrals, and we just say that f at the endpoint here minus f at the start is equal to our line integral. And that you will just get from the following, and then the k's cancel out and you will get what your line integral is, and you will get an answer. So that's just basically how the fundamental theorem of line integrals helps us quite a lot if your function of f is conservative. Later we'll learn a bit more about when it's a three-dimensional function and how to prove if it's conservative then. But for now, for two-dimensional vector fields, that's how we prove how they are conservative. And this is the end of the theory parts for theme 3.3.